Alright, welcome. This is our very first video for kinematics. Now remember that AP Physics is broken up into 6 or 7 big ideas. And we're not really going in a specific order. Big ideas are just big ideas. So the first big idea is we're going to cover is the one, number 3. The interactions of an object with other objects can be described by forces. And there's a lot that goes into that. So we're going to be spending a large part of this year with big idea 3. So we have our learning goals here. The first one basically talks about motion, all the, talking about it, doing math with it, graphing it. The second one is all about, getting, how do you conduct experiments with motion? If I were to conduct an experiment, what data would I need to collect? How would I look at the data? The next learning goal is all about projectile motion, which, to be perfectly honest, is almost identical to the first learning goal. Projectile motion is something that's going to seem scary, but really it is not. It's nothing to worry about. It's really easy. And then finally, relative motion. We're going to be doing a little bit with this one, but I'm not going to spend a whole lot of time with relative motion because I just don't think it's going to show up on the exam. And if it does, it would be like 1 question out of 50. So I'm not too worried about the relative motion. We'll cover it, but I'm not doing a whole lot with that. All right, so kinematics, what exactly is it? It's kind of a big fun word, kinematics. All it is the study of motion. So what we have is we're going to have an observer in a particular reference frame that can describe the motion of an object using quantities such as position, displacement, distance, velocity, speed, acceleration. And there's all kinds of things we can do with that. Now, you'll notice sometimes I have stuff that's italicized. This is the essential knowledge from your AP Physics 1 curriculum. I just pulled this right out of the curriculum. So displacement, velocity, and acceleration are all vector quantities. So displacement, velocity, and acceleration, these are vectors. So what in the world is a vector? Basically, this is a quantity that has both magnitude and direction. I probably still haven't answered the question though. What is a vector? So something that has magnitude and direction. Magnitude is a measurement of some kind. So for example, the velocity of a car. Now notice I put a little tiny arrow above that V, and I do this little weird tail for my V because I don't want the velocity V to get confused with a volume V. But the vector for velocity would be something that has magnitude. So let's say 6 meters per second. So that's its magnitude. At 17 degrees north of west. Okay, so here we have the magnitude, and here we have the direction. And that is a vector, something with magnitude and direction. On paper, we use an arrow. So if I were to make a plot of this velocity here, north, you guys probably know the compass, north, west, east, and south. It always spells out the word we, and it's north of west. So this velocity right here would be an arrow that's 17 degrees north of west and has a magnitude of 6 meters per second. So that would be that velocity right there. That would be a representation on paper. And we'll do more with vectors. I'll have some non-graded laboratory exercises using protractors and rulers where we'll get some practice with vectors. They're really, honestly, not that bad. Okay, displacement. is the first thing I want to talk with you about. Displacement is a change in position. Velocity, we're going to learn, is the rate. Now, rate means something over time. Is the rate of change of position with time. And acceleration is a rate, so again, something over time, of the change in velocity with time. Changes in each property are expressed by subtracting the initial value from the final value. So let's unpackage that a little bit. Displacement then. We use a delta x for displacement. It is a vector, and it is equal to the final position minus the initial position. So I use a little tiny not symbol. It's a subscript O for my initial values. So if I were to take a look at, let's say, a football game, and let's say that the ball starts on the 10-yard line, it's carried to the 40-yard line, but then it's brought back to the 45-yard line. The displacement would be its final position, which would be 45 yards, minus its initial position, which was 10 yards. So that equals 35 yards. Now notice, this is a displacement, it's a vector. I've given you the magnitude, so I need a direction. So let's say that everything, this direction is north, so it's 35 yards north. So there, now I've got a vector. I've got my magnitude and my direction. Now notice this is different than distance. The distance is the total ground that the ball is covered. So going from 10 to 40, so it's 10, 20, 30, 40, 50, 60, 65 yards. And distance is a scalar, so you don't have to give direction with that. So that is like distance versus displacement. And it's not too bad. All right, the next thing is velocity. And we have constant velocity. That's the first thing we're going to start with. So it's an even change in an object's position over time. Position is simply an object's location at a certain time. So again, I think football fields are great examples for this. So let's say an object has a velocity, a constant velocity of 5 meters per second, starting at a position of 0. So with that knowledge, that means then at 0 seconds, the object is at a position of 0 meters. At 1 second, the object has a position of 5 meters. After 2 seconds, the object has a position of 10 meters. And I'm just going to keep going until I get to 20 meters. And I stopped at 20 because I want to make a graph of this, and I've got a 20 by 20 grid graph here. So whenever you look at motion graphs, the x-axis is always for time. Okay, so I got 20 lines, 4 seconds, so 20 divided by 4 is 5. So for every 5, 1, 2, 3, 4, 5, so that's 1 second. 2, 3, 4, 5, that's for 2 seconds. 3 seconds, 1, 2, 3, 4, 5. 4 seconds. On the y-axis, we're going to put position. And I'm measuring that in meters. And I got a position of 20 meters. This is 20 boxes, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20. And now I'm just going to go through here, and I'm going to plot this. So at 0, I have zeros. At 1 second, I've got 5 meters. All right, so let's take a look at this data then. I hope that you can see that this is a clear example of a linear relationship. So, if I draw a line of best fit, now when you do this, use a straight edge like a ruler of some kind. I'm going to freehand it, so mine's not going to look very good. But when you do this with pencil and paper, use a ruler or something to draw a straight edge. A line of best fit is a straight line or a line of some kind of relationship that goes through as many data points as you can. All right, that's not perfect, but it's not too bad. Okay, since I have a nice straight line, I want to find its slope. Now, what I do is I pick 2 points on the graph. Now, do not use data points. Choose 2 brand new points. And I look for crosshairs, so like that one right there and that one right there. Try to get them as far apart as you can. Then I like to draw a right triangle on my graph like that. So, slope, y2 minus y1 divided by x2 minus x1. So my y2 looks like I have 18 meters minus my y1, which looks like 3 meters. My x2, it looks like it's, see, each line here would be worth 0.2, so 3.4 seconds minus 246.6. So the slope then looks like that's going to be 15 meters divided by, let me grab a calculator, I'm not very prepared right now. As you get older, you stop being able to do arithmetic as easily in your head. So 3.4 minus 0.6, so that gives me 2.8. And when I do 15 divided by 2.8, I get 5.3 meters per second. So I think you see that I should have gotten 5 meters per second. But you know, keep in mind, I freehanded this one. I think if I were to use a straight edge, the data would have come out and gave me a nice slope of 5 meters per second. But you know, that's experimental data, so that's not too bad. So looking at this then, we see that the slope should be the same thing as the velocity. So when you have a position versus time graph, the slope gives us velocity. So looking at this then, we see that the velocity equals the final position minus the initial position divided by a final time minus initial time. So if you look at your y2 and your y1, you should see that's like an x minus an x naught, and your x2 and x1, that's really time. That's, you know, t minus initial time. So that then gives us delta x over delta t. So velocity is that right there. Okay, so remember, whenever you see a graph, the 2 questions you need to ask yourself is, what does the slope represent and what does the area represent? So here, slope represents velocity. Area, the units for area would be a meter multiplied by a second. There is nothing. The area is meaningless for this one. So you don't have to worry about the area for a position versus time graph. Now, again, since this line is straight, it's a straight diagonal with slope, the object has a constant velocity. If we were to graph constant velocity on a velocity versus time graph and on an acceleration versus time graph, what would those look like? So let's do that. So on this one, I'm going to have a velocity versus time graph. Well, if the velocity is constant, it's not changing, then that means that this velocity here would be a horizontal line. So looking at this, we can see then that you know, it's not changing. Okay, now slope on this line. Slope would be velocity divided by time. Okay, that's acceleration. So any slope on this graph would have acceleration. The area would be velocity multiplied by time, so that's meters per second, time second, so that's meters. So any area under this line would give us displacement. So looking at this line, the slope equals 0. So if I were to take a look at an acceleration versus time graph, since there is zero slope here, there is zero acceleration. So the acceleration would be 0. Alright, we will conclude with this video on this one right here, since we're approaching 15 minutes. So that concludes video 1.